Hi again, everyone. I'm going to have a little look at a topic that I've been requested to do a video on, and now take requests. And it's an extension to the momentum topic that some of the earlier videos were on. And it's in relation to a particular style of exam question that does come up from time to time, quite often in the multiple choice, which when you see the amount of background work and it goes into it, always surprises me and seems to be a little bit harsh. But it's to do with the concepts of the momentum transferred by fluids, i.e. liquids or gases that are in motion. The questions, the way they're worded is quite often the bit that causes the most confusion. Asking for something like the change in momentum per second or the transfer of momentum per second when a fluid hits a surface. And there's a couple of particular contexts that we're going to have a look at, just sort of review both, but there's a number of different things they could ask. One question, one common one that comes up is in terms of a helicopter. So here's Harold. Okay, and the idea being, well, basically how a helicopter works, as the blades rotate, there will be a column of air beneath them that is pushed downwards. So the blades are actually pushing air downwards. Then by Newton's first law, the air then pushes the helicopter upwards. Okay, nice and simple. But because as they go around, they are prescribing a circle, then the column of air that is pushed down will be almost cylindrical. It's never quite perfect, but it'll be a cylindrical column of air underneath that's forced downwards. So knowing the velocity of the air as it moves downwards, it will then impact, say, on the ground or a surface, and we can work out the momentum that is transferred to the surface per second. Now I'm going to come back to that point in a second. The second concept that's quite often covered is in the terms of something as simple as a hose pipe, which might have a fluid such as water running through it. And again, usually circular in cross section. So as the water comes out, it's a cylinder of water, okay, that comes out. And again, some knowledge about the flow rate or the speed of the water. And then you might be asked what momentum it transfers to a surface that it impacts on coming out at a certain speed. Okay, so what we're going to do is just break these questions down and look at what they're usually asking. So as I've mentioned, they usually ask for the transfer or change in momentum per second. So they're not asking directly what is the momentum of the water or what is the momentum of the air. Okay, they can ask that about a single particle, but for a fluid, it's quite difficult to actually ask that directly with the momentum of a fluid because there's a large mass going through and it's a continual flow. But if we look at what that actually means, if we are looking for a change in momentum, okay, now you might remember from an earlier video that the change in momentum, which is also called impulse, is force multiplied by time. Okay, so change in momentum is force multiplied by time. So the change in momentum per second, what these questions are really secretly asking, but not using this word, is what's the force applied on the surface by that fluid. So it's a bit of a sneaky question, and that's what you've got to look out for. Now I'm going to continue with although technically we now know we're looking at the force on a surface, okay, what we're going to do is I'll keep it in terms of momentum per second so that gets in your head, because that's what sort of appears on these exam questions. Okay, so just going to break down how to deal with them, okay, the long way. So that you can see where these things come from. Then there's a couple of equations at the end that essentially I would advise you to learn. They're not on the formula sheet, but if you learn them and they come up, you'll be sorted and you can do these questions really, really quickly. You might common sense your way through them a little bit. It's quite often how people do pick up, just having a look at the numbers that they give you and realising that going through the long derivation is clearly going to take too long. But if you do just know it, that's even easier still. Okay, so just as a recap, momentum. We know momentum is mass times velocity. So momentum per second, or the change in momentum per second, is mass times velocity divided by time. Okay, so we're doing it per unit time. Now I'm going to deliberately put the T under the M rather than the whole thing. It doesn't make any mathematical difference, but what we're going to discuss here is something called mass flow rate. How much mass of fluid, whether that's water, air or another fluid, how much of that fluid in terms of mass passes a point per second. Okay, and that can be quite difficult to measure. So what's easier to measure is the volume of fluid that comes per second, and we know that mass is density multiplied by the volume. Just a quick note on my notation, simply because there's a lowercase v for velocity and a capital V for volume, I've just put the lines across the top, the bars across the top, just so that you can be really clear about which one's which in this, because they're going to appear in the same equation in a second. Because we can substitute that into here. So we've got our change in momentum per second, or transfer of momentum per second. We'll substitute mass out and replace it with rho v. We've got the little v, hence why I'm just trying to make sure they're clear which one's which, and that divided by time. Okay, so I've got density multiplied by the volume of fluid per second. I'm going to treat that as a single term in a second, multiplied by the velocity of the fluid. Now there is a notation for V over T, volume flow rate, or volumetric flow rate as it's more commonly known. Okay, and in some texts, but it's not an actual AQA sort of spec thing, but in some texts that's given the symbol Q, where Q is the volumetric flow rate. It's simply the volume of fluid that flows per second. Okay, and that simplifies our equation down to change in momentum per second, density times volumetric flow rate times the velocity of the fluid. Okay, now the issue with that is it's very unlikely that you will get both volumetric flow rate and velocity given. Usually, and you'll see why in a second, there's not much point in doing both of those measurements because they're very, very closely linked together. In fact, they're linked together simply by the cross-sectional area. So actually they can be replaced with each other quite readily. So I'm just going to move Harold out of the way for a second. Pop him over that side. Okay, so if you imagine, I'll use the hose pipe as an example here because it's a little bit easier to think about. So if we were to draw our cylinder, so imagine that's the hose pipe, and then out of the end we've got a column or a cylinder of liquid, or it could be a gas again, but a fluid nonetheless, coming out of that. I'll just draw that in. Okay, and there is our volume of liquid per second. If that was in a time of 1 second, so that fluid had gone from the opening to there in 1 second, so we'll call that 1 second. The length of that column, okay, would give us a little bit of information that links volume, okay? So if we just say, right, so the volume of that cylinder of liquid that's emerged in a second, that would simply be given by simple geometry, the cross-sectional area of the cylinder, multiply by that length, okay? Now again, you're very unlikely to measure that length, but we're not actually interested in the actual volume. What we're interested in, if you remember, is the volumetric flow rate. So if I was to if I was to looking for the volumetric flow rate, all I've got to do is that's volume divided by time. So if I do AL over T, okay, volumetric flow rate is just the volume divided by time. So I've just divided that by time to get that. L over T, length divided by time, that's the velocity. So this simply becomes AV. Okay, so just to make that absolutely clear, Q is the cross-sectional area, so volumetric flow rate is cross-sectional area multiplied by the velocity. Really, really neat and simple. And a rearrangement of that, because we're going to use that in a second, is therefore velocity is volumetric flow rate divided by cross-sectional area. And because the cross-sectional area is constant, okay, you can easily switch between volumetric flow rate and velocity, which is why back down here, you're not likely to measure both because they're really, really closely linked together by the cross-sectional area. So depending on what the question actually asks, what numbers are given in the question, our momentum per unit time can be worked out from one of two equations, and it does depend what they give you. So if the question quotes velocity of fluid, okay, we know that momentum per unit time is rho q v, density, volumetric flow rate, velocity. Okay, and if I'm given the velocity, I don't know q, but I can substitute in for q, look, because q is a times v. So that means I get rho times by a times v times by v again. So this simply comes down to be rho a v squared. Really simple. Not on the form sheet, something you might want to learn. Okay, so remember the force on a surface from this, that's what that is. Transfer of momentum per second is density multiplied by cross-sectional area multiplied by the velocity of the fluid squared. If, on the other hand, you are given the volumetric flow rate, which sometimes they will give you in a question, so the question quotes volumetric flow rate, again, we're just going to substitute in. Starting point's the same, rho qv, but now we're going to say we don't know the velocity, so I'm going to substitute in q over a. So I've got rho q, and instead of velocity, q over a, and you can see that really simply simplifies down to rho q squared over a. Downside of this, there's two equations, neither of which on the formula sheet. You can sometimes just pick it out when you see it. Like I say, it's in a multiple choice often, so you've got to be quite quick at picking this up. But there's the way to actually go about doing it. Okay, so what I want you to leave you with that is just a little bit of practice. Okay, so I'm going to put up just two questions. Okay. So here's two questions. We've got, okay, on the left, a helicopter with a blade diameter. The numbers, I don't know if they're real or not. Please don't quote me on any of these, whether they're realistic. I've just made up the numbers so that you can have a go at the questions. So we've got a helicopter with a blade diameter of 15 meters. It displaces air downwards at a velocity of 300 meters per second. Calculate the change in momentum per second. Again, that would assume that it's hitting some sort of surface on the way down. Given the density of the air, 1.2 kilograms per meter cubed. Okay, the density of air, remember, will vary depending on atmospheric temperature, atmospheric pressure. So it's that is actually a variable, so you've got to make sure that you use values that are quoted. Second question looks at the hose pipe, and of course this one we're given a velocity in that question. Second question, we've got a hose pipe context, diameter of 3 centimeters, watch out there. Water flows from the pipe at a rate of 2 times 10 to the minus 4 meters cubed per second. This time we're given a volumetric flow rate. Calculate the momentum transferred per second by the water when it hits the surface. Density of water, 1,000 kilogram per meter cubed, assuming that that's therefore pure water as it's going through. Have a go at those. Okay. Once you've done them, pause the video, or pause the video first, might be useful. Pause the video, have a go. And then in a couple of seconds, I'll flash the answers up for you. Okay, so there's the answer to those. Work through simply using those two equations we've just come up with in the previous part of the video. And we've got an answer of 1.9 times 10 to the 7 newtons and 0.057 times just 0.057 newtons. With units, you have to be careful what the question asks. You know, it might ask for it in terms of units of momentum, which is Newton seconds. But if it's momentum per second, it's Newton seconds divided by seconds. Officially, that is just newtons. So, but you might be tempted to write Newton seconds per second in the answer, which is fine so long as it's absolutely clear. If it's multiple choice, okay, just be aware they might put it in Newton seconds because they've specified in the question it's per second. So they can be a bit sneaky there as well. But there's the solutions, work them through, check your answers, and hopefully that will solve that little dilemma for you.